Well, all right, here we go. So, new chapter today, starting in on chapter 7. Tempting to say this is the last chapter we're going to cover, but it's not. Remember, we skipped chapter 4. We will be going back to chapter 4 at the very, very end of the course. But anyway, we're making progress. So, chapter 7, we're going to be talking about sort of three-dimensional versions of the theorems that we've just seen in 2 dimensions. Concerning line integrals. These next theorems are going to be about surfaces. We are eventually later today, going to be defining surface integrals. But in order to be able to do the computations we need to talk about how to parameterize a surface. So that's our first big topic for today. So it's actually a lot like a parametric curve. Remember, the idea of a parametric curve is that position is a function of one parameter. A parametric surface, position is a function of now 2 parameters. A very, very similar idea, in other words. Now, of course, because there are 2 parameters, the domain is R2 or some subset of R2. Right? And if you think about it, then if there's 2 parameters, the image will itself also be 2-dimensional. There's sort of, in some sense, 2 different directions you can go in your inputs, and so you would expect 2 different directions you can go in your outputs. So here is a nice sort of starter example. This is what we call a parametric plane, and y'all have actually seen this before. We talked about parametric planes back in chapter 1, section 1.5. So you can flip back in your notes and take a look at that. The big idea, I'll remind you, is that if you have this vector v1 and this vector v2 that are parallel to the plane, but not parallel to each other, of course, then you can use those to talk about, for example, how far would I need to go in the v1 direction. That, of course, would be some multiple of v1. And then perhaps how far might we need to go in the v2 direction. And, of course, that's going to be a multiple of v2. Right? And then given a starting point, let's see. We'll start. I've used a lot of colors here. I'll start at red. Given a starting point, x naught. Right, you can see that x naught plus the dark green plus the dark blue gets me to anywhere I could need to be in that plane. Right? And just by tweaking the parameters, keep in mind that s and t are my parameters. So tweaking s controls how far I go in the v1 direction. Tweaking t controls how far I go in the v2 direction. I can get anywhere in the plane I need to be. And this will trace out the entire plane. Everybody happy? All right. So this is our first example of a parametric plane. And again, notice 2 parameters, s and t, and with position in space being the result. Right? And so this is a surface in space. Okay. Now, how do we... I'm getting a little ahead of myself. Sorry. One other comment that I want to make about this. Given that there are now 2 parameters, we do have to abandon one of our earlier perspectives on parameterizations. So parametric curves, of course, there's only 1 parameter, and with only 1 parameter, we have the flexibility to say, hey, you know what? I'm just going to view my parameter as being time. All right? Very reasonable. But now that we have 2 parameters, I can't have them both be time. That's one of those really confusing sci-fi movies. It's hard to follow, right? That would be a weird idea. So it's really not a useful idea to think of these as being time. Now we just are going to revert to, they're just parameters. They're inputs that allow you to change your output. So don't try to think of the time point of view on these. Okay. All right. And with that now said, let's talk about how to create parameterizations. So very similar to my favorite parameterization for curves, is my favorite parameterization for surfaces. It is the graph parameterization. I think this is fantastic. It is super duper useful. I don't want to say it's the only parameterization tool. It's not. There are some others that we will talk about, but it is the most commonly the best one in at least some sense. So the big idea, if you have a graph, now notice here, z is a function of x and y. That makes this a graph specifically, and it does have to be a graph. The big trick is, whatever your input variables are, let those be your parameters. That's it. That's the big trick. Whatever the input variables to the function whose graph you're looking at, let those input variables be your parameters. Everything else will just fall into place. After all, if x and y are s and t, and then I plug that into this equation here, and that forces z unavoidably to be that, and we're done. We have position as a function of s and t. That's parameterization. Everybody on board? Everybody see this? The same trick, right? As parametric curves, graph parameterization. Same trick, just adapted to this new circumstance. Okay. All right, now in this example, I had z being a function of x and y. There's nothing magic about alphabetical order. You can kind of have any variable being a function of the other two. Doesn't matter. Same rule applies. Whichever variables are your input variables, let those be your parameters. So here, in this next example, I've got x and z being my input variables. So x and z are my parameters, s and t. Okay, now there is a twist on this example. This example here, you'll notice that none of the variables is currently written as being equal to a function of the other two. Right? So you do have a kind of some decisions to make, choices to make. Which one do you want to try to view as being a function of the other two? Problem is, I can't solve for x or z in this equation, right? It's you can't. It's transcendental. It's out of the question. The only reasonable thing to try to solve for is y, and it is pretty straightforward to solve for y in there. And then I have, as planned, y is a function of x and z, and as previously noted, if you plug in what x and z are, this then forces y to be what it has to be. Everybody see what happened? Okay. Okie dokie. All right, so here's another version of this. This is a sort of a coordinate system, alternate coordinate system version of this. You don't even have to have solved for one of the rectangular variables. You can solve for any variable in any coordinate system in terms of the other two variables of that coordinate system. And the same basic trick works. So here you'll notice I have what we might call a spherical graph. Right? Rho is a function of phi and theta. Now, it's a temptation to look at this and say that is not a function of theta. But yeah, sure it is. It's just really boring function of theta. It is still a function of phi and theta. So that noted, I am going to let phi and theta be my parameters. You'll notice I didn't even have to rename them as s and t. They're already not x, y, and z, and thus there's no renaming necessary at all. So I'm just going to leave phi and theta as my parameters, and you can rename them as s and t if you want to, but it doesn't. It's not essential. And so, with that being the case, that forces rho to be whatever it is. And then notice, as required, we have position as a function of the two remaining parameters, phi and theta. Everybody good? Okay. All right. this next method is a little weird. It's might even call it obscure. It is a nice little mental exercise, though, so I think it's worth talking about. We saw some examples with parametric curves where you can use vector algebra to simplify otherwise hard problems. You may recall that the example we did concerned a bicycle. We had a bicycle wheel, it was rolling down the street, we're looking at the reflector, and we've all seen the little weird, jumpy, twitchy pattern that the bicycle reflector makes. How do we parameterize that path? And the big trick was to realize that that difficult to understand vector was a sum of two much simpler vectors. Okay, so I've created a weirdo scenario here where, roughly speaking, the same thing applies. And here's the deal. So we're going to start off with a graph. Easy graph, by the way, chapter 2 methods, right? This has got rotational symmetry around the z-axis. Make sure you're good with the idea that that's what this looks like, right? Flashbacks to chapter 2. And that I can parameterize pretty straightforward, right? So this point right here, any point on that graph, I can construct with the graph parameterization, and so that, that part's easy. Okay, that's not the surface we're interested in. The surface that we are interested in is what results if you were to imagine that every point on this green surface is the top of someone's head, right? And there's hairs coming out of their head. All the hairs are going to point perpendicularly. So imagine that they've grabbed onto the static electricity thing. The hair goes like this. And all of the hairs protrude perpendicularly to the head, to this graph. They all have length 1. Right, and what we're interested in is what is the shape of the resulting sort of the tips of the hair. In other words, what does this person's head kind of look like as a result of the hair? Does that make sense to everybody? Okay. All right, so how do we parameterize the purple? The big idea is to say that, this purple point, a point on this desired surface, let's see here, the surface H, in other words, is, it's a point on the green surface plus this unit normal vector. Right, so roughly speaking, all we're going to eventually write down is that purple is equal to green plus blue. And it's just going to turn out that green we've already got. I mean, here's a formula for the green point. Right, and we're going to have not that much trouble, as it turns out, to write down the blue vectors, and green plus blue is going to give us purple. Everybody see the big picture strategy? Let's talk about how to find these blue vectors. The big idea is to rewrite this equation. Oh my gosh! To rewrite, you know what? I'm going to delete a bunch of stuff. Rewrite this equation, currently written as a graph. One variable is a function of the others. We're going to rewrite it as a level set. Right? It is a level set of this function. Right? It's what you get when you set this function g equal to 0. Right? So it's a level set of that function g. And level sets, I have this this nice feature that gradients are always perpendicular to level sets. So I can just take the gradient of this function little g here, and that'll give me a vector that points in exactly the direction that little n is supposed to point. And of course, the way we get little n then is to just normalize. Right? Keep in mind that we're talking about hairs of length 1, and so thus we normalize the dark blue vector to get the light blue that we actually need, which is this. Everybody okay? And it's all over at this point. Let's see here. Okay, yeah, here we go. So remember, the big idea is that points on the surface we're interested in are going to be the sum of the green, easily parametrized green points, right? And then these blue, normalized normal vectors representing the hairs. Yep.
Why a sum?
Oh, well, yeah, because that's what's going on. If you look at this picture right here, right, this is what it means to add a point to a vector, or add a vector to a point, you might say. Right? So another way to think of it is you could imagine that this green point, okay, here we go. Imagine that the green point is a vector coming out of the origin, and that the resulting purple is also a vector coming out of the origin. So viewed as vectors, you can now pretty literally see green plus blue is purple. Is that cool? Yeah. So just a reminder to everybody that, yes, all points can be, all points are, have an associated position vector. Right? You can think of them as vectors for convenient purposes sometimes. But it's nice to be comfortable with the idea of what it looks like without reconsidering it as such. And so I like the idea of having an idea in your mind of what it means to add a point in a vector, and this is what that looks like. Yeah. Oh. Right. Okay, moving along. Now this next one is not obscure. This next one is a pretty common scenario to find yourself in. So this is an important trick. Sometimes the foot in the door to creating a parameterization is to create a coordinate system. You're going to create your own brand new coordinate system, tailor-made for your incidental purposes. Right, and so let me just show you an example of how this could play out. So let's suppose we're interested in this thing we call a torus. It's basically a donut, right? In particular, it's the surface of the donut. It's where the glaze is. And how would I parameterize this surface? It's not a graph in any coordinate system that we previously have, anyway. So what are we gonna do about that, right? How are we gonna actually create a parameterization here? Also, not clear how I would view this as a sum of easy vectors, right? That would be kind of hard. So here's the idea: coordinate system. I'm going to create a coordinate system as follows. I'm going to kind of imagine that this is a weird world that we somehow live on or in, right? And how would we talk about where we are if we lived on a planet that was that shape? Right? And we wouldn't have the same notions of longitude and latitude. There is no North Pole, right, or South Pole. So something's going to have to be different. But nevertheless, I would propose that I still think a couple of angles would be a pretty handy way to describe location on this strange planet. Right? And the idea is that there is a kind of a longitude-like thing, namely how far, let's say going counterclockwise as seen from above, counterclockwise around the edge, how far until you get to where you're at, right? And then there's also the question of, I should do this, starting from sort of the middle of the dough, how far do you have to sort of angle upward from the equator? Right? And every point on this surface is going to be described by a combination of those two angles. So, for example, this point right here, right? You get to that point by, going up by some angle t, and then kind of around by this angle s. Everybody see what I'm talking about? This is not the only way to do it also, right? There's other options. You could think creatively, other coordinate systems that might be useful here. I think this one's going to be hard to beat, but nevertheless, there's nothing required or essential about this. We're making this up for our purposes. Okay, so that's really going to be our foot in the door. And what I'm going to do then now is just use these angles and some geometry to just literally write down the coordinates of this point. Right? And it's a multi-step process here in order to get to that point. The first thing I'm going to do is observe that, well, let me go back to my original picture. I'm going to observe that this orange point here is a little bit easier to write down. That orange point is going to be computed as follows. It's going to be this vector, which is constant, plus then this vector, and that vector, of course, well, that depends on what your T angle is. That's what sort of goes around, if you will, going around the handle of the donut. So that's going to be a function of T, and a little bit of trig and geometry gives that blue vector is that right there. Now, again, a little bit of geometry involved there. Is everybody confident they can follow through that geometry? Make sure to take the time, look through, persuade yourself that this is what that is. Okay. And so that gets us to our orange point. That gets us to this thing that I'm calling P. So P is this thing. All right, so then that's not what I wanted. Of course, what I want is the purple point, and so now I'm going to make the observation that I can get to that purple point by way of doing a rotation. I'm just going to rotate counterclockwise by this angle S. Rotate counterclockwise around the z-axis, and that will rotate the orange into the purple. Does everybody see that? Let's write that down. Let's write that down. So again, we have this orange point already computed. Previous discussion. The rotation claim is done by this matrix. We'll come back and talk about that matrix in a moment. And again, that's how I get to what I wanted. The point that I wanted, the purple point, is just the rotation of that vector P, as seen here. Okay, now what is this rotation matrix and where did I get it from, right? How do I know that this is the rotation matrix? Well, I'm going to remind you, Math219, linear algebra, right? Rotations are linear transformations, aka matrices, aka they're understood by their columns, which of course are the images of the standard basis vectors. So you're going to find this matrix by understanding these columns one at a time. Again, good exercise. Make sure you can do it. If you have any trouble, come to office hours. I'll be very happy to talk you through it. I want to make sure everybody's good with this. But I am going to assume in class that you're proficient with that kind of stuff. Okay. All right, so there. Now you got to multiply it out, and here you go is your parametrization of a torus, aka a donut. Everybody happy? All right. So now it's easy to get lost in this example. There's a lot going on. There's some trig, there's some linear algebra, there's some geometry, right? So the big idea of this example, the whole reason I brought up this example, though, is just as a reminder, we started with this question of how do I parameterize a torus? And the foot in the door, the thing that allowed us to even get started in the first place, was we created a coordinate system. I let S and T be these coordinates as figured, because it seemed reasonable and natural in this context. Having these coordinates, which ended up being my parameters, was the foot in the door. Everything else is details. Everybody with me? All right. Okay, moving along. Sometimes you already have a parameterization of a similar surface. It's not quite exactly what you want, and sometimes all you have to do is tweak your existing parameterization to get the parameterization you want. So here's an example. We know that the unit sphere is parameterized like so. Now how do I know that? This is a spherical graph parameterization. This is where I took rho equals 1 and I plugged it in where the rho was into the existing sort of standard, spherical coordinate conversion formula. So that's just a spherical graph parameterization a la 2 pages back. All right, so we have, again, for our existing sphere, we have a parameterization. Now, I like to think of parameterizations as sort of vector formulas, position vector as a function of parameters. You don't have to. You could think of it as individual coordinates. Individual coordinates that are functions of the parameters. It's the same thing. It doesn't matter. I'm writing it in both different ways to kind of give you a couple of different points of view on what I'm about to do. Okay. All right. So now, here's the big question. I have now an ellipsoid that I want to parameterize. How am I going to parameterize this ellipsoid? Bad news. The equation in spherical coordinates is, oh my gosh, it's really weird. It's very hard to write down. Not particularly convenient. Right? And then, let's see here. It's hard to figure out how I'd view this as being, sums of vectors. It just doesn't break down in any particularly obvious ways. So what I'm going to do then is I'm going to recognize that there is a relationship between the equation for what I have and the equation for what I want. And I think the relationship here is pretty clear, but just to be blunt, for example, everywhere I had an x, I'm replacing it with x over a. And likewise for the y and the z. Right? So this is the deformation. This is one of the pieces, anyway, of the deformation. We have this existing parameterization of the sphere. I know how I need to deform that to create the thing I actually am interested in. Now, so what do I do about this deformation? Replacing x with x over a. I know what that does. I know that stretches in the x direction by a factor of a. And so you can think of that in two different ways. The sort of the obvious way to do that is to just literally in the equation over here, just where you see the x, literally replace that with x over a. Hard to argue with that. I mean, if you replace x with x over a in the equation, well, then you're going to do so everywhere else, of course, also. Right? So that's one point of view. Here's another way to think about it. This process of replacing x with x over a, we know that stretches by a factor of a in the x direction. We know, in other words, that all of the x coordinates are going to get magnified. All of the x coordinates are going to be a times as big. In order to account for that, dividing by a business in the equation. And how do you make the x coordinate a times as big? Well, we're going to take our existing parameterization of the sphere, and I'm going to literally make the x coordinates a times as big. That make sense? Okay. So kind of take your pick on how you want to think about that. You can think about it as a substitution, or you can think about it as a stretching suit yourself. These are equivalent, of course. I mean, the equation. The equation x equals a times blah 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 is totally equivalent to this equation here. It's just the a kind of got moved around to the other side of the equation. Nothing's really different. Cosmetically, it kind of looks a little different. And it's easy to get that backwards. So heads up, please pay attention carefully to which of these sort of points of view you're taking, and don't accidentally multiply when you should divide, or vice versa. Right? It's easy to get that wrong. But certainly, though, algebraically, these are equivalent equations. Okay. Everybody happy with this example? Likewise for the y and the z, of course. Okay. All right. Okay, so there are a bunch more examples in the book. I will point out that all of the book examples interpret existing parameterizations. All the book examples say, hey, here's a parameterization. Let's try to figure out what the surface looks like. You'll notice all of my examples have been, here's a surface, let's try to figure out what the parameterization is. So all of our examples are kind of backwards of each other. I think my examples are more relevant. Most of the time, a surface is going to come to you in some random way. It'll just be described as, oh yeah, it's a sphere of radius whatever, or it's a plane that blah, 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 right? It's going to come to you generically. And the problem will be to create the parameterization. So that's why all of my examples are in that format. But it is also a healthy exercise to think about it the other way. So look at the book's examples as well. Okay. All right. So we're going to sort of play around with our new idea of a parameterized surface now. There's some nice work that we can do that's going to end up with a nice punchline. So here we go. I'm going to define something called coordinate curves of a parameterized surface. It's a pretty simple idea, really. If you have two parameters, but if you then fix one of them, right, let's suppose that we fix t. Whoops. Man. Suppose that I fix t. T is now constant. T is not allowed to change. Well, wouldn't you say then that now position is really no longer a function of two free parameters? There aren't two free parameters. One of them, t in this case, has been fixed and is not allowed to change. Now I have position as a function of one parameter, and position as a function of one parameter is a parametric curve. Let's see, I'll do that in yellow. Everybody buy it? I mean, here's a weird way to say it. If you have a function of two variables and you make one of those variables not a variable, well, now you have a function of one variable. 2 minus 1 is 1 is a point of view on that. Okay. All right. So this is called a coordinate curve. This one, for example, where we fix t, that gives you the s coordinate curve of that parametric surface, because s is the remaining variable. Okay. All right, let's see an example. So I'm going to go to the sphere for this example, and recall we just got through talking about this parameterization of the unit sphere, right? That's our unit sphere. And let's see here. We're going to look at this specific point. We'll do this in dark blue. So this specific point right there. That's the point where phi is equal to pi over 6. Theta is equal to pi over 4. Right? And, okay, so what I'm going to do then is I'm going to fix one of these parameters. Theta and phi are our parameters, and I'm going to fix one and then interpret the corresponding coordinate curve. That's a function of the other. Okay, so let's fix, doesn't matter, let's fix phi as pi over 6. All right, so phi is not allowed to change. I'm going to then have theta be my variable. Theta is allowed to change. Theta can vary, a little less, a little more than the starting point, pi over 4, right? But phi is stuck at pi over 6. So what happens then over here on our picture when I do that? Well, phi is stuck at pi over 6. Theta starts to, decrease or increase. get that right there. This is what we call our theta coordinate curve because position's a function of theta. Everybody with me? All right, and of course we could do this the other way around. We could say, let's fix theta. Theta is now fixed, pi over 4. Theta not allowed to change, but I'm going to allow phi to change. Phi is allowed to get a little bigger, a little smaller, whatever. And with constant theta, let's see here, constant theta, but phi being allowed to change, I will get that curve right there. Everybody happy? Yep.
Does coordinate curves have an orientation?
Yeah, all parameterized curves are implicitly oriented in the direction that of the increasing of the parameter, right? So as t increases, let's see. As phi increases for this curve, as phi increases, the direction that the curve goes as phi increases is the orientation on that curve. Yeah, right. This applies for all parametric curves. Yeah, good question. Anybody else? Okay, so let's see here. Yeah, right. So the next observation. Now this is kind of a matter of thinking it through. I want to talk about this line right here. Partial derivatives of the parametric surface are velocities of the coordinate curves. Let's think that through carefully. How do you get a partial derivative? I ask rhetorically. You get a partial derivative by step 1, holding the other variable constant. Oh, well, okay, but hey, if you think about it, if you're holding the other variable constant, that creates a coordinate curve. Okay, so step 1 of partial derivatives is to hold the other variable constant. In other words, look at a coordinate curve. Step 2 of a partial derivative is to take the derivative with respect to the other variable. So taking the derivative of the now only variable for that parametric curve, for this coordinate curve, and taking a derivative with respect to the only variable gives you velocity. Right? So it's just a kind of a matter of terminology, really. But both of these things, so taking a partial derivative of a 2-parameter parameterization is the exact same as taking the velocity of the 1-parameter parameterization that results from holding the other one constant. Again, it's all just, it's the same words ordered maybe a little differently. Does everybody buy it? Okay. So, partial derivatives such as this and this. Those partial derivatives are velocities. And velocity times input change gives you output change. So with those being the velocities, if I, for example, were to imagine let's see here, color choices. If I were to imagine a little d phi input change, right? Multiplying that d phi input change times the velocity gives me times the velocity, aka the partial derivative, gives me the corresponding output change. Right? So as always, input changes turn into output changes. That's what a derivative is, most fundamentally, a relationship between input changes and output changes. In this case, having the velocity gives us exactly what we want. Okay. All right. So now, why are we doing this? What's the point? Where are we headed? You will notice, perhaps, that if I look at this differential there and that differential there, between the two of them, they make up the sides of a little parallelogram that's approximating a piece of the surface. that surface area, that tiny little piece of surface area, right, is very closely approximated by this little parallelogram, that parallelogram having edges defined by those two vectors. And so if I wanted to compute how much area there is in that little piece of surface area, I would just take these two orange vectors, apply chapter 1 rules, Math219, right, old linear algebra rules, and boom, that gives me that area. So as seen below here, again, so this little piece of surface area, I claim is computed by this formula, where I'm going to take my two edge vectors, that one being that, for example, and this one here in red, just for color contrast, being this one, right? The area is the magnitude of the cross product. Let's see here. Yeah, so the magnitude of the cross product gives me that area. Is that cool? All right, so that's really nice, and then I can do a little bit of algebra here, and now make sure that you're good with the algebra of cross products and the algebra of absolute values, of magnitudes. But when you have a scalar factor in one of the vectors, that scalar factor will factor right out of that cross product. And it also, as long as it's not negative, will factor right out of the magnitude calculation. And so this d phi just factors right out. And likewise, this d theta factors right out, thus giving me now a different formula for, again, this piece of surface area over there. That little piece of surface area is this. But what's nice about this reformulation is that I am now viewing my piece of what you might call the output piece of area as being a multiple of the input piece of area. Oh my gosh, wait a second. Now I have a rule that tells me how much to multiply by the green input area to get the yellow output area. This is starting to sound familiar, right? This is a lot like the ideas that we saw when we were doing change of variables. It's different. It's dimensionally different, of course, right? Change of variables is always 2 dimensions to 2 dimensions, or 3 dimensions to 3 dimensions. This one's 2-dimensional input to 3-dimensional output. So this is not a change of variables as we formulated them previously. But I mean, strategically, it's a lot. I mean, this is playing the role of a stretching factor, just like in change of variables. Does everybody see that? This is an unexpected sort of like, oh my gosh, we just stubbed our toe on something pretty useful here. We now have a stretching factor strategy for computing surface areas on parametric surfaces. Okay, cool. All right, now there's some notation stuff to talk about, and this is a little bit annoying. So here's our stretching factor. You'll notice that our stretching factor is the magnitude of a particular vector. The cross product of the partials of the parameterization. And I've got that written in terms of phi and theta because we were looking at that specific spherical example just as an example. But in general, that is generalized by this general form here, xs cross xt. This vector gets used a lot, not just as the vector whose magnitude gives me the stretching factor, right? But also for other purposes that we're going to see as we go further into Chapter 7. So it turns out this thing I have highlighted in green, turns out it's kind of a big deal. We're going to need to talk about this. So I'm going to give this a notation. This is a pretty standard notation to call it capital N. We use n because this vector, if you think about it, it's a cross product of two vectors tangent to the surface. So in fact, this capital N thing is normal to the surface. It is perpendicular to the surface. So it's a normal vector. Thus the capital N. I like to call this the parametrized normal vector because, let's face it, there's actually a lot of normal vectors, just different directions. They all point along the same line, perpendicular to the surface, right? But different magnitudes and possibly going the other way, perpendicular to the surface. There's a bunch of different normal vectors. This specific one here is the one that comes out of this specific parameterization. So when you have a parameterization, I think it makes sense to call this the parameterized normal vector. Now, FYI, our book makes a different choice here. Our book calls this the standard normal vector instead of the parameterized normal vector. All right. It's just words, right? It's nothing to get upset about. But my quibble with this choice of words here, calling it standard, is it makes it sound like it's intrinsic to the surface. And it's not. Right? This, what I'm calling capital N, what I'm calling the parameterized normal vector, is intrinsic to the parameterization. There's lots of parameterizations. Every parameterization will give you different parameterized normal vectors. I think it's weird to have a bunch of different things that you all call standard. Right? I don't know. I think that weirds me out. I'm not a fan. So anyway, I will be calling this the parameterized normal vector. Be aware the book will call it the standard normal vector. We're talking about the same thing, different terminology. Yes?
Is this equivalent to the normal vector of the tangent plane at a point?
It is a normal vector to the tangent plane of the surface. Yeah, absolutely. But it's not the only one. There's a bunch of, if you think about it, right, here's a plane. There's a bunch of vectors that are normal. There's varying different lengths, or maybe down this way, right? So it is a normal vector. It's normal in the same sense, right, as you intended in the question. Yeah, right. But there's the key point is that there's a lot of them. Okay. All right. So so this is our formula for our area stretching factor when we're looking at a parameterized surface. So let's use this to compute a surface area. We're going to compute the area of the unit sphere. Now, this is a formula that you've seen in high school geometry classes, probably, and there are ways to compute this with single variable calculus as well. You can view the sphere as a rotated surface, for example, and you can make some clever arguments there. So I'm going to use this to reproduce the result that we already know using this multivariable calculus technique. Okay, so first, talking about the unit sphere. There's our parameterization of the unit sphere. We've seen this is our third time seeing it today, right? Same one. Real quick, coming down to the bottom, the total surface area is the sum of all these little pieces of surface area. And as we just discussed, surface area is stretching factor times parameter area. All right, so here's that formula that we saw before. Here's our stretching factor, right? And so this should be our formula for how to compute that surface area. Is everybody on board with just that little part there? Okay, now of course we're left now needing to know what this stretching factor is. I need to know the magnitude of capital N, and here's where we have to take a deep breath and just plow forward. Now I have done this multiple times in my past life. It's your turn. I think everyone should do this. Work out these details. It's not that bad, but this is a pretty standard calculation. It's a healthy exercise, so I would encourage everyone to do this. I've hit the highlights of it for you here, just to make sure everybody follows the right process. But here we go. Parameterization. We take the appropriate partials. We take the cross product of those partials. Right. Well, there's some algebra to be done there, but it's not that bad. Here's that cross product. That's your capital N vector. Of course, the stretching factor that we're interested in is the magnitude of that capital N vector. Right? So you're going to have to take this whole thing and compute its magnitude, and yes, it's annoying. The Pythagorean identity shows up heroically several times and turns what would otherwise be a nasty expression into this wonderfully convenient little result, sine phi, as it turns out. It's really nice how that works out. Again, healthy exercise. I think everybody should do this once in their lives. Give it a shot. Is that cool? Okay. All right, and so now it's kind of all over but the shouting. Here's the stretching factor that I've inserted into there, where we previously discussed that area. It's the sum of all the little pieces of area you chop it up into. Output area is stretching factor times parameter area. And so we've just got to compute these integrals. And, of course, these are easy integrals. This d phi integral right here, no sweat, nothing to it. Right? And then, of course, the result is a constant, and that makes this outer d theta integral actually really easy. And the nice, convenient punchline is the answer we knew we should have gotten in the first place. Everybody all right? Yep.
Is the normal vector equivalent to a parameterization of the gradient? Because it's, or like a gradient for you guys, like if you're viewing the second level sense.
Yeah, no, I know what you mean. So no. So I hear where you're coming from, and so you can create a normal vector by reinterpreting your parametric surface as a level set, taking the gradient of that function whose level set it is. Right, that will give you a normal vector. The problem is it will not give you the same normal vector. And again, the problem here is that normal vectors are not unique. Right, there's lots of normal vectors. So this one gives you a normal vector. This method you described gives you a different normal vector, and they're different, right? So they are multiples of each other, right? And that's nice, but the issue is that that magnitude is actually important. In fact, the magnitude for the moment is the only reason we care about capital N in the first place. As of the moment, we will eventually also care about the vector itself. But so the magnitude is the key point, and so we can't just choose something that has an arbitrary different magnitude. Yeah, it's a great question, but this is different. Yeah, right. Okay, so now this next page, or at least this top part of the next page, is just kind of a summary of all the participants in this conversation that we just had, the players in this little story that we've just discussed. So in general, when you have a parameterization, you have input parameters, right? And that gives rise to coordinate curves, whose velocities we can talk about. Right? And those velocities give rise to the edge vectors of this little differential piece of area, right? Which we can relate to our parameter differential piece of area. And, of course, the relationship, as we've discussed, is this stretching factor, the magnitude of capital N being a normal vector, being as it is a cross product of two tangent vectors. So, anyway, there they are. These are all the players in this story. This is largely just kind of a reproduction of what we've already written down. Nothing new there in that algebra. All I've done next is to point out that, you could take these velocity vectors, these partial derivative vectors, you could write them out in coordinates, right? Nothing happened there when I did that. And then this cross product, you could kind of crank out that cross product and something kind of neat happens. Something a little eyebrow raising. As you take that cross product, mysteriously, the coordinates of the cross product are two-dimensional change of variable stretching factors. Isn't that surprising? Seems a little coincidental, right? Anytime in math when there's a coincidence, it makes it seem like there may be something going on, something underlying. And there is, and I would love to talk about it, and sadly not something that we have time for in Math 219. If this were a year-long course, I would absolutely do it. It's a pretty cool conversation, actually, but we just don't have time for it. So, anyway. If you're curious, come to office hours. I'll be happy to talk about it. Okay. Now, there's a special case that I think is worth noting. The special case concerns the conveniences of if you have a graph. And again, keep in mind, you might get the impression from hearing me talk that I don't like graphs. This is not true. I love graphs. What I don't like is people assuming things are graphs when they aren't, right? This is a big problem, right? So don't overinterpret from the wonderful properties of graphs, right? That's what sort of gives me the willies. But graphs are super. Graph parameterizations are super. And here's one of the great things about a graph parameterization. That is that the structure of this calculation works out the same way in pretty much all of the possible cases. So, for example, if you have a graph, and if you write down the graph parameterization, there it is. That's what it is. It's always going to look exactly like that. Which means that the partial derivatives are always going to look exactly like that. Right? I mean, you're always going to have just an S here whose S partial will always be 1 and whose T partial will always be 0. Likewise for the second coordinate, right? That's just very convenient. It's always going to work out nicely like that. The cross product of these will always be that. Simple calculation. And the magnitude of this cross product will always be, well, let me do it like this. It'll always be, you know what, just let's take this one step at a time. It'll always be this. Pretty easy to see. And then you notice that these two terms right here will always be magnitude squared of the gradient. And they just are. Right? The function f, its gradient, has explicit coordinates, and lo and behold, I mean, that is literally magnitude squared of the gradient. And wait a second, magnitude of the gradient is steepness. Old chapter 2 result. Just is. So, how about that? This is pretty cool. Neat calculation. The upshot is that anytime you're using a graph parameterization, whatever function you're looking at, right, your stretching factor is always a nice, simple function of just one question: how steep is your graph? That's it. Just the steepness of the graph contributes. So, nice fact. Now, how are you going to use this? Most of the time, this formula right here is the plug and chug winner. This is the one that generically that you kind of most convenient, because typically if you have this function, you typically don't already have the magnitude of the gradient, so you might as well just start with this anyway. But it is really useful sometimes to know this connection to steepness, and this next example that I have is a great example of this. So let's talk about putting a roof on a house. And by the way, we just did this at our house. And you would not believe how expensive it is to put a roof on a house. It's mind-boggling how much that costs. Now, you want to make sure that you don't get overcharged, because a little bit of overcharge could be thousands of dollars, right? One of the big costs of putting a roof on a house is the shingles, right? The actual, or whatever they call them, Shingles, is that what it is? Yeah. So the actual materials that make up the roof of the house, right? Well, how many shingles are you going to need? Well, you need to know the area of that roof. And if you think about it, a roof, is a graph. Which tells me right away that if I want to do a computation of the area, if I want to know how much area there is up here, boom, I can write this down immediately because it's a graph. Is that cool? So, okay, well, now, why am I writing this in terms of steepness? Well, here is I guess I'll call this a architectural fact is an overstatement, but a trend, a very common convenience in architecture. Very often, they'll make roofs in such a way that the steepness is constant. So the same amount of steepness, even though there's a bunch of different faces over here, right? Bunch of different faces. What's that? 1, 2, 3, 6 different faces. They're all the same, pitch, maybe you call them. They're all the same steepness against the horizontal. And why they do that, I couldn't tell you exactly, but it's surprisingly consistent. And of course, obviously, every house is different, and some have cool architectural. You got your gables and your, awnings. Or it could be cool different things, right? But very, almost uniformly, but not quite, constant steepness. So if you think about it, then constant steepness. If this is a constant, then that means that this whole expression here is a constant. Constants factor right outside of the integral, leaving you then only with integral dx dy, namely the footprint area. And why do we care about this? Well, it turns out, if you think about it, the footprint is usually made up of a bunch of rectangles. Rectangles are super easy to compute the area of. A tape measure and a calculator will allow you to compute the footprint area of your house, no problem, right? So combine that with this observation we've made on the left, and you can compute the surface area of the roof, which, if you look at the geometry there, would be a much harder problem, right? How to compute that surface area? Well, okay, first of all, I'm going to have to figure out what is that length. What is that length? And I guess I could get up on top of the roof with a tape measure, but I'm going to confess I am not doing that. Right? I'm scared. It's high, right? A 2-story house with a crawl space. It's at a attic, and it's like 40 feet up there. I'm not doing that. Okay. And then there's stuff like this here, where even if you know the lengths, right? I mean, there's the question of what is that angle, and it can turn into a really weird calculation to compute the area on your roof if you get up there and do it on the roof. But you don't have to. All you need to know is how steep is it, and what's the area of the footprint. And both of those are easy. So anyway, that was cool. Nice little sort of everyday application of multivariable. Okay, questions? Anybody? Everybody happy? All right. Okay, so we're going to move on and talk about surface integrals now. It's a lot like line integrals. Really is. So let me flash back here, by the way. Here is a... I guess I'm a little too far ahead. Here we go. Line integral. The big idea is if I have a curve, that's what I like to call dimensionally awkward. Right? It's a one-dimensional thing, but it lives in a two-dimensional world, or maybe even a three-dimensional world, and double integrals don't make sense. Single variable integrals, not really. It's just weird, right? It's a different scenario, and so we tailor-made a Riemann sum to address the very natural idea of taking this curve and chopping it up into a bunch of little pieces and saying the whole is the sum of the parts. Chop it up, add it up. Right? So Of course you would. And then we invented a notation and a terminology to go along with that Riemann sum. Okay, we're going to do the same thing now for surfaces. A surface in space is dimensionally awkward. It's intrinsically a two-dimensional thing. It has area. It doesn't have volume. It has area. It's a two-dimensional thing. But it lives in a three-dimensional world. So again, our existing notion of double integral doesn't really make sense because it's curved. How do you deal with the curvedness of it? And triple integrals certainly don't make sense. There is no volume in the question at all. So we need to make a new notion of a Riemann sum. And here it is. We're just chopping up this surface into little pieces, as shown. And just making the observation that on any given little piece, whichever little piece we might be looking at, quantity per unit area times area should give me quantity. Right? So if I've got, for example, mass distributed across this surface, or maybe this is a mountainside and I've got flowers growing on the side of the mountain at varying density, and I want to count the flowers. Whatever it is, right? Quantity per unit area on each little piece times the area of that little piece tells you how many flowers there are in that little piece, and then you just add those all up. Does that make sense to everybody? Just strategically. All right. So, the notation we're going to use is this. I think it's pretty believable, right? Area, represented by ds. Two-index summation, represented by a double integral symbol. Pretty believable notation, I think. We're going to call this a surface integral because it's an integral over a surface. And I hope it's plausible if I call this a scalar surface integral because the differential is a scalar, namely area. The integrand is a scalar, namely quantity per unit area. It's a scalar notion of quantity. So mass or flowers or ants or whatever. Everybody with me? Okay, so scalar surface integral. Now again, why do we have to be fussy about calling it specifically a scalar surface integral? Well, a little foreshadowing, just like with line integrals, it's going to turn out there is another kind of surface integral that we're going to see really soon. I don't think we'll make it today, but we might. It's coming up real quick here. But there is a different kind of surface integral, and we need to distinguish the two from each other because they're structurally significantly different. So, okay, here we go. How are we going to compute that? Again, we're going to rip off an old idea. How did we compute scalar line integrals? Well, we used parameterizations as a tool for pulling back the integral defined on our dimensionally awkward curve to an integral defined on, well, the t-axis. Right? So parameterization was what we used to do a pullback. And we had an existing setup of named, objects and participants. It was a pretty easy calculation to follow through. So we're going to do the same exact thing here. We're going to take our idea of a parameterization of a surface, right? And we're just going to use that as a tool for pulling back. Namely, I'm going to rewrite a surface integral. Let's see here. I will do this in red. So I've got an integral on this surface. I don't know how to do integrals on surfaces. Oh, they're all curvy and wiggly and stuff. And so I don't know how I'm going to compute that surface integral. Well, I'm going to just rewrite it as an integral that happens over here in the ST plane. Just a pullback. Is that cool? Details to follow. The details are largely a matter of plugging in. F, previously a function of x, y, and z, with x, y, and z now being functions of s and t, all together plugging in, F is now a great big function of S and T. That's just plugging in. That's all it is. Plugging in the formulas that the parameterization gives you for X, Y, and Z. And then there's this business about the area and what is the relationship between output area and input area. Well, old news. Our stretching factor we already computed last time. There's our stretching factor, the relationship between input area and output area. Cool. Notice how it's, morally or strategically or whatever you want to call it, it's really, really ripping off the old solution that we came up with for parametric curves. Okay. All right. So now let's do some. Oh, and then real quick, this is a formality. By the way, the book spends a bunch of time and effort establishing this fact. You're not responsible for all the details that go into establishing this really cool fact. But even though the parameterization appears explicitly there and implicitly here, even though the parameterization is part of this expression, the value of that expression will be independent of what parameterization you pick. So if you pick one parameterization, you pick a different parameterization, it doesn't matter, you're going to get the same answer. Parameterize however you like, it doesn't matter. Gotta love it. Okay. All right, so now let's do one. I'm going to pull a move similar to what we did again with line integrals. Remember the first thing I did was I did kind of 4 parallel examples, right? Because all of these examples we're using the same wire, parameterized by the same parameterization, which therefore had the same velocity and therefore the same stretching factor. So a tremendous amount of the computation in all 4 of these examples, tremendous amount was the same stuff over and over again. So likewise here, I'm going to consider a upper unit hemisphere as my surface. Right? So kind of a dome. Right? And I have mass distributed across that dome, where the mass per unit area is higher, the higher up you go. This is weird, but one could imagine. And given that shape, let's compute the mass, let's compute the coordinates of the center of mass, and let's compute the moment of inertia around the z-axis. So a bunch of different calculations, but we know we're going to need the stretching factor in all of them. And conveniently, the unit sphere, the unit hemisphere is part of the unit sphere, and we've already done this calculation for the unit sphere, so we already know our stretching factor is going to be sine phi. I say, we've already done it. What I mean is I've already done it, and y'all are going to do it per this, right? So you got to fill in these blanks, confirm that sine phi is the stretching factor. Okay. Okay, so then here we go. Mass, the whole is the sum of the parts. Let's see, the x-coordinate of the center of mass, weighted average of x. Totally different computations we're doing, but notice in both cases, dm shows up. dm in both cases is mass per unit area times area. Is that all right? Yep.
But when I think of center of mass in terms of like 3D, I think of it as like over a volume, that we find the center in the volume. But then, how would it work?
That's a reasonable question. For two-dimensional center of mass, we define it as where would you put your finger underneath it so that it would balance, right? With 3 dimensions, I can't exactly do that, but there would be an analogous idea of if I have my surface here, right? And if I know the center of mass is at a particular point, then if I were to imagine taking that surface and freezing it and then having the ability to support it, even though it doesn't include that point, just pretend like there's a little balsa wood structure underneath that allows me to actually support it at that center of mass point, that it would balance at that point. Yeah, that's right. And furthermore, that would be the case no matter how you rotate it. Yeah, right. Anyway, it's got the same formula as we've previously seen. Okay, so mass is mass per unit area times area. Area is stretching factor times pullback area. Stretching factor we just computed was sine phi for both of them. Let's see, what do we do with all these other things in here? Well, let's see here. This is green. Don't forget that, what colors have I used? I've already used orange. Okay, so don't forget x is this thing right here, sine phi cosine theta. This is the plugging in part that we were talking about. So x sine phi cosine theta. Right? Z, right there. Z is cosine phi. Here, why don't I do this real quick so we can, there we go. Z, cosine phi. Everybody with me? So once you've got your stretching factor and your parameterization, it's literally just a matter of plugging into the standard formulas for these things, and we end up with our pullback integral. So notice these, of course, are different pullback integrals. Here's the pullback integral to compute mass, and then here is the pullback integral to compute the x-coordinate of the centroid, and then likewise for other coordinates, and likewise for the moment of inertia. It's all kind of same sort of thing. Yep.
So this parameterization is in spherical coordinates. So if the parameterization is in rectangular coordinates, is there an extra factor?
Nope. So I hear where you're coming from, because you're accustomed to when you hear in spherical coordinates that you have to throw in a factor of rho squared sine phi, right? But just keep in mind where that rho squared sine phi came from. That came from recognizing that you were doing a change of variables. That was your stretching factor for change of variables, right? And the thing is, we've already got that. This magnitude of capital N here, that's my stretching factor. That accounts for the fact that phi and theta aren't the same as the, you know what I mean? And so that is the stretching factor. So you've already by virtue of this right here, you've already included your stretching factor. Is that cool? Okay. All right. Okay, so I'm going to draw the line right here. We're out of time. It's actually a really good place to draw the line, and we will pick up here on Monday. Wait, Monday? No? Oh, right. Monday's a holiday. Okay, so see you Tuesday and have a great extended weekend. Nice holiday. Okay.